Okay, class, welcome back. We are now going to transition from laboratory safety to laboratory data. In this video, my main objective is that you will be able to use significant figures in determining the reliability of data, along with being able to write numbers in scientific notation. And saying that, let's dive into this video. The main reason we discuss these topics in chemistry is because we need to be accurate and precise in providing data for our experiments. Accuracy is how close a data point is to a desired standard. If I'm an archer, the goal of archery is for me to hit the bullseye. To be considered an accurate archer, my arrow would have to consistently hit that desired standard of the bullseye. You can also think of it this way. If I'm an accurate shot in basketball, then I'm going to consistently make the ball within the goal of the basket. In other words, count on me to score points for the team. Precision is probably not exactly what you thought it was. Precision is the closeness of multiple data points. For example, if I'm a precise archer or basketball player, I may or may not hit the desired standard time and time again. But whatever place I hit, it is going to be close to my other shots. In other words, if I am precise, my actions are repeatable or replicable. When it comes to laboratory experiments, this means all my trials produced are close to the same result time and time again. Once again, those results may or may not be close to our desired results, but they are at least close to each other and replicable. So what does this have to do with chemistry and other science classes? Well, in order for data to be considered valid in science, it must be close to a desired standard and it must be replicable. In other words, we must not only be accurate, but we also must be precise. If the pharmaceutical industry was not accurate in their dosages or precise, then they could be facing a never-ending supply of lawsuits of drug overdosage and ineffective medication. Now that we know the differences between the precision and accuracy, let's talk about how science presents data. What better way to start off than introducing scientific notation? Scientific notation is a way to represent extremely large or small numbers. Scientific notation consists of three parts: a mantissa, a characteristic, and a multiplication sign. A mantissa is a number greater than or equal to 1.0 and less than 10.0. The characteristic is the number 10 raised to the power of an exponent. And that exponent will tell us which way to move the decimal in the mantissa to create the number in standard format. We will go more into that in a second. So, when writing a number in scientific notation, we need to write the mantissa multiplied by the characteristic. Now let's talk about taking numbers from standard form and making them into scientific notation. So, let's take the number 2,500 and convert it to scientific notation. My first step in this type of problem is to create a mantissa. In order to do this, I'm going to have to add a decimal place at the end of my 2,500. So, 2,500 decimal. I then need to move my decimal place either to the left or right, making an appropriate mantissa. Remember, a mantissa is between greater or equal to 1.0 and less than 10.0. So, in this case, I'm going to have to move my decimal place 3 places to the left to make a mantissa of 2.500 or 2.5. Next, I add my multiplication sign and my characteristic. The exponent of my characteristic is dependent on which way I move my decimal and how many places I moved it. If we move the decimal to the left, our characteristic's exponent is positive. And if we moved our decimal to the right, the exponent of our characteristic is going to be negative. In this case, we moved our decimal place 3 places to the left, so our exponent should be a positive 3. This means 2,500 in scientific notation would be 2.5 times 10 to the positive third power. Let's do one more. This time, let's do the number 0.000543. To make this a mantissa, we're going to have move our decimal place 4 spots to the right. This would make our scientific notation 5.43 times 10 to the negative 4th power. Okay, so now we can convert numbers to scientific notation. How do we convert it out of scientific notation? Well, the first thing we're going to do is look at the exponent of our characteristic. If it is negative, I'm going to move my decimal place to the left as many times as stated by the characteristic. If it is positive, then I'm going to do the opposite. Any open spaces, I place zeros in. So if I am wanting to convert 5.43 times 10 to the negative fourth power to standard notation, I would look at my negative 4 and move my decimal place 4 places to the left, making sure I fill in any open spaces with 0. This gives me the number 0.000543 as my standard notation. Okay, let's work another one, and let's say I give you 2.5 times 10 to the third power. Since it is a positive 3 as my exponent, I'm going to move my decimal place 3 places to the right. This gives me 2,500. These are the numbers we've already worked with, so now you can see how we went from standard to scientific notation and from scientific notation to standard notation. The last type of scientific notation problem you might see is correcting any incorrect versions of scientific notation. So this basically tries to give you a problem in a pseudo or fake scientific notation. Basically, this means I give you a number that is not in proper mantissa form, multiplied by 10 raised to some sort of power. To fix this scientific notation, I'm going to have to make a proper mantissa form. In other words, I'm going to have to move my decimal. If I move my decimal to the left, I would add however many places I moved it to my exponent, and if I move my decimal to the right, I would subtract that from my exponent. So, if I had 254.55 times 10 to the third, then I would move my decimal place 2 places to the left, thus adding 2 to my exponent, giving me the correct scientific notation of 2.5444 times 10 to the fifth power. For the sake of working another type of problem, let's say I have 0.023 times 10 to the fourth power. I would move my decimal place 2 places to the right to make it 2.3, and I would subtract 2 from my power. This would give me 2.3 times 10 to the second power. Okay, that should be enough with scientific notation. Now let's jump into our last topic of the day, which is significant figures. So finally, our last topic of the day is significant figures, and honestly, it's not too bad. The first thing you need to know with significant figures is the general rule for counting digits, which are significant. The easiest rule for sig figs or significant figures is the rule of non-zeros. Basically, it states anything that is not a zero is significant. So the number 1, 2, 3 has 3 significant figures: the 1, the 2, and the 3. Next, we need to discuss our zeros. Okay? So there are several rules when it comes to zeros in significant figures. Our first one is all leading zeros are insignificant. In other words, they do not count or are not counted. So in the number 0.0012, there is only 2 significant figures, and those only come from our non-zeros. Anything in front of our non-zeros that are zeros do not count. The next type of zero we can talk about is our sandwich zeros. These are zeros between 2 non-zeros, and they are always, 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 always significant. So, in 101, we would have 3 significant figures: 2 non-zeros, which are our 2 ones, and 1 sandwich zero, which is our zero in between our 2 non-zeros. The final type of zero that we are going to talk about is our trailing zeros. A trailing zero is any zero after the last non-zero number and is only significant if there is a decimal point. So 100 does not have a decimal point, so it only has 1 significant figure, and that would be the 1, which is a non-zero. While 100.0 has a decimal point and has 4 significant figures. Because of this decimal place allows us to have the 3 trailing zeros to be significant and our 1 non-zero to be significant. Now we know our significant figures, we can talk about how do we use them in data. Well, the main situation I want to emphasize is when having to use mathematical operations with scientific data. In order for scientific data to be considered valid, there are rules in which we must follow in conducting mathematical operations with measurements. I like to think of these as the rules of the weakest link. Like a team is only as strong as their weakest player, scientific measurements are only as valid as their weakest measurement. So how do we determine these weak links? Well, for adding and subtracting data points, the rule is for identifying our weakest links are the following. 1. Count the significant figures to the right of the decimal place for each number. Whichever number has the least amount of sig figs to to the right of the decimal place is your weakest link. Next, or 2, we add or subtract our numbers. And then step 3, we round our answer to the total number of sig figs of our weakest link. So if I add 122.40 and 5.702, I would first count how many sig figs I have to the right of the decimal for each number. This means 122.40 has 2 sig figs to the right, and 5.703 has 3 sig figs to the right of the decimal. This means 122.40 is our weakest link. We will keep that number in our mind for later. Now we add these numbers up and we get 128.102. Now we round our number to our weakest link. So since 122.4 is our weakest link, it has 5 significant figures, 4 non-zeros, and 1 trailing zero. This would mean my answer would have 5 digits in it. So I count my places and see that my 0 will be my last digit in the 128.102. To see this round up or down, I look at the number next to it. If it's greater than 5, then I round up. If it is less than 5, I round down. Since our number after our 0 is 2, we are going to round down. This gives us a finished answer of 128.10. Okay, our last rule for this video is multiplying and dividing significant figures. These are super easy. These rules for determining the weakest link is the number with the least amount of sig figs overall. So if I multiply, so just like our addition, our weakest link determines how many significant figures are within our number. So if I multiply my 5.26 times 6.1, I would see that my 6.1 has 2 sig figs while my 5.26 has 3. This means my 6.1 is my weakest link, and my answer will have 2 sig figs in it. Now all I have to do is multiply my answers and round to 2 sig figs. If I multiply out, I get 32.086, which rounded to 2 sig figs is 32. Okay, I think that's enough for today. Though no single thing we talked about was exponentially hard, we did cover a lot of topics. So if you need to go back and rewatch any portion of this video, please do so. And saying that, keep up the good work in the classroom and see you next time.